There we go. It's now recording lesson 11. Okay, so what this does is it gives us a reasoning for wanting to create an operation that takes two vectors and creates a vector that is perpendicular to both of those vectors. Okay, so that's our goal today, is can we come up with an operation that takes any two vectors, say in this case here the vectors 2, 4, 6 and 1, 4, -2, and produces a third vector which is perpendicular to both of these two vectors. All right, so that's the goal. So before we try to think of this as an operation, let's see if we can actually calculate such a vector. Okay, so what I want you to do is I want you to think about how could you come up with a vector. Okay, and the idea here is not to do guess and check, is to come up with a process you could follow that finds some vector. You know, a little hint here that maybe if you don't know what that vector is yet, what might you call it? What would we call this vector that we don't know? Okay, yeah, call it U. And in particular, since we're dealing in 3D and we seem to be dealing with algebraic vectors, how do I want to represent this vector U, this unknown vector U that I'm looking for? There you go. Describe it as an algebraic vector, say x, y, z. Okay, so your goal is to figure out a plan, and you don't even necessarily need to get to the end of this. Okay, if you can, that's great. But figure out a plan. How would you determine this vector x, y, z? Okay, that's going to be perpendicular to both the vector 1, 4, -2 and to the vector 2, 4, 6. So just try to start up that process. Think about how you would calculate such a vector. All right, so I'll give you a minute or two to think about it, and we'll come back. All right, so we're back. Let's take a look here. So give me some ideas. How would I start this process if I'm trying to determine a vector that's going to be perpendicular to both of these two vectors? What would be my starting point? What could I make use of that would be useful for me here? Okay, looking for ideas here. I have this vector. Say I call this vector here U, and I call this vector, say W. Sorry, let's call it V. I'll use W for the other one. Say vector V, and I'm looking for some vector W. That's going to be perpendicular to both those two vectors. You know what? I don't even think I need to talk about vector projection. I think that's even more complicated than I need to think of. Not unrelated, not unrelated. There you go. Let's go even simpler. I mean, in the end, it produces the same thing that you're talking about, Samya. But yeah, what I need is I need the dot product. I need W dot U to be equal to 0, and I need W dot V to be equal to 0. Okay? So if we take, W dot U, so here we have, X, Y, Z dot 2, 4, 6 equals 0. What does that give us? Well, it gives us this equation, 2x plus 4y plus 6z equals 0. Okay? And then if I take W dot V, so X, Y, Z, this vector here dotted with vector V, 1, 4, -2, I would need that to be equal to 0. So in other words, I need X plus 4y minus 2z to be equal to 0. So I would need both of these equations to be satisfied. Okay. Now, even before we start to try to, solve this system of equations that was produced, can you sort of see that there's a bit of an issue here? What's the issue here with these two equations in the unknowns that we have?
You only have two equations and you have three unknowns.
You got two equations, you've got three variables. Now, we already know we should know what happens when we've got, say one equation with two variables. So that might already give you a sense of this part of the equation, or this part of the question is this going to be unique? Now, the other thing is, remember what we have is you've got these two vectors and you want to come up with a vector that's perpendicular to those two vectors, I mean, you can probably figure out that there's more than one vector that's perpendicular to these two vectors. So we probably should be expecting more than one answer. So let's just see what happens here when we try to solve. So I guess, I'll use elimination here. So I've got, I'll keep equation 1 as it is, 2x plus 4y plus 6z equals 0. And I guess I'll multiply equation 2 by 2. So I get 2x plus 8y minus 4z is equal to 0 again. And I guess I'll subtract these two. So the x's cancel out. So what do I end up with? Well, I end up with negative 4y is 6 plus 4 is 10 plus 10z is 6 plus 4y plus 10z is equal to 0. And so here, I can't really solve for either y or z. The best I can do is solve for one in terms of the other. I guess I could solve y is equal to 10 over 4, 5 over 2z. Okay, that's about as good as I can get here. All right. So, what does one do once one does part of the solution? What might I do with this relationship that I just found? Any ideas about what I might do with this now? What would be the next step in an elimination problem if it was two equations and two unknowns?
You could replace z in the original
There you
equation.
go. Do the substitution. So, I guess I'll pick this one here. Okay, so what do we have? We have x plus 4 times, well, y can be written as 5 over 2z, minus 2z equals 0. So what do we have? We have x, so 4, 2. So we have, looks like we have 10z minus 2z. So x plus 8z is equal to 0. So x is negative 8z. So it looks like we've kind of shown that we have infinitely many solutions, because here w, okay, our vector xyz could be any vectors as long as, well, we need, such that, y is equal to 5 over 2z and x is equal to negative 8z. How many such vectors are there? There's infinitely many. If I picked z equals 1, well, one of my vectors, call it w1, would be, well, z equals 1, so I guess negative 8. Y would be 5 over 2. And then z would be, well, we picked it to be 1. There's one vector that's going to be perpendicular to both. Let's pick another easy one. Let's pick z equals negative 1. 8, negative 5 over 2, negative 1. Well, wait a minute. Does it make sense that if this vector is perpendicular, that its opposite would also be perpendicular? Let's see. There's my two vectors. If this vector is perpendicular, does it not make sense that the opposite vector would also be perpendicular to those two? Okay. And you start to realize that there's infinitely many possibilities. You might even think about what is special about all those different possibilities. Okay, we will get to that later on. So we see here that there is a way to determine vectors that are perpendicular to two given vectors. Okay, and we use the dot product. And there you go. We can find as many as we like. Who would like to tell me why I'm not particularly happy at this point? I mean, you'd think I'd be excited here. I just found a way to do something new. Why am I not particularly happy about what I came up with here?
Because you have infinitely many possibilities.
No, that doesn't bug me that much. Hey, I got choice. Nothing wrong with choice. There's something that bothers me way more than that. Yeah, look at how much time it took just to find, even just one of these vectors. That's way too much effort. okay, to determine something that I'm claiming is going to be an important operation for us. Okay, so this again, as sometimes I do, is I try to do this to give you an inspiration to find something that's much more efficient. Okay, so let's keep this in mind. But before we go to kind of looking at how we might do this in a more efficient manner, I just want you to, since we've done 3D, that's definitely the harder one. What I want you to do is I want you to now reproduce this in 2D. Okay, so here's two vectors, and I want you to algebraically show me how you would come up with a third vector that's perpendicular to both of those two. Okay, so we're back here. So curious to see what you came up with here, but let me just follow the same process as before. Let me take, W dot, I'll call this first one U, okay, and make that equal to 0 since I want this vector to be perpendicular. So let's just write it out, just like it'd be 2x plus y equals 0. And then if I do the same thing with vector V, what do we end up with? Well, we end up with negative x plus 3y equals 0. So again, I end up with a system of equations. And this looks good because I actually have two equations and two unknowns. But what happened when you tried to solve that? Did anything interesting happen? You realize that the solution to this equation is just 0, 0. Okay, x equals 0 and y equals 0. Now you could either see it by recognizing, if you think of these as two lines, well, these two lines both pass through 0, 0, so that must be the point of intersection. They're definitely not parallel to each other, but even if you tried to solve it, 2x plus y equals 0, and then let's multiply this by 2, negative 2x plus 6y is equal to 0, and you add 7y equals 0, there you go, y equals 0. And when you input this back into one of the equations, you're just going to get x equals 0. So that doesn't make much sense, the vector 0, 0. But what I want you to do, though, is I want you to think geometrically. Okay? Say I've got my Cartesian plane. And let me pick, two vectors, whatever they look like. Say these are my two vectors, u and v. Well, if I try to pick a vector that's perpendicular to this one here, can it possibly be perpendicular to the other vector? No. Pick any other two. Let's pick even maybe two that, look like this. If I find a vector that's perpendicular to one vector, there's no way it can be perpendicular to the other. Same thing here. If I find a vector that's perpendicular to this one, there's no way it's going to be perpendicular to the other. And all of a sudden, you realize that this idea of finding a third vector, which is perpendicular to two given vectors, is not a reasonable question to ask in 2 dimensions. Okay? It certainly is in 3 dimensions because, as we said, here's my two vectors. It makes sense that I could find a third vector that is perpendicular, to both those vectors. All right? And so this process, this new operation that we're going to be defining right now, okay, is a bit of an oddball operation because up until now, everything we've been defining has been defined so that it works in 2D and 3D and 1D. Presumably can even be expanded if I start to consider this idea of 4, 5, 6, 7 dimensions, whereas this particular operation that we're going to define is a purely 3D operation, okay? So it has some very nice applications, certainly in terms of physics, but we're going to see that even in terms of that analytic geometry that we're going to do a little later on. This idea of defining a vector that's perpendicular to two given vectors is going to be very, very useful for us. All right? So something to keep in mind, that this is going to be the one operation that we're going to define, which is purely a 3D operation. Okay? It has no meaning, no sense in 2D, and certainly not in 1D. All right? So let's actually look at what this operation is going to be. And I will tell you right off the bat, this is one of those things that I'm not going to actually prove. It's a little sort of long in terms of the algebra, and I don't really think there's too much use in doing the proof. If you're interested, you can take a look at the textbook. It does go through it, okay? But what I'm going to do here is I'm just going to define this operation, okay? And then in the next example, we'll just check that it does give me what it needs to give us with an example, okay? Certainly it's not going to be a proof, but it'll give us a sense that it does work, all right? So I think I had referenced this before. This is that other product that I was talking about. So far we have the dot product, okay, which takes two vectors and produces a scalar quantities. And in fact, we're already seeing the importance of it and the usefulness here. Okay, so just to give you a sense of how we would come up with this cross product that produces this perpendicular vector is I would do exactly what I did here. Okay, exactly what I did here. Okay, I would, start, let u be equal to, x1, y1, z1, v be equal to, so instead of a specific vector like we had back in number 1, I take two general 3D vectors and I would, look for my vector w such that it satisfied the two conditions, that w was perpendicular to u, in other words, the dot product was 0, and that w was also perpendicular to v. In other words, that dot product is equal to 0. Okay, and if you follow this process through, you would come up with a formula for not the vector, because remember, how many vectors do we expect to be able to satisfy these conditions? We expect there to be infinitely many possibilities, all right? So essentially, they chose one of those possible scenarios to be what we call the cross product, all right? So the way we define this cross product, now you'll notice here, and it's very important that we use the notation correctly. So here, the dot product, it's called the dot product, and the symbol has to be a dot. What we're going to be defining here is called the cross product, as somebody was happy that we got to it. So the cross product of u and v, okay, also known as the vector product, and you can imagine why, because the result now is not going to be a scalar quantity, but it's going to be a vector quantity, all right? So assuming these two vectors here, the way we define the cross product, okay, and as I'm writing down the definition, you'll start to see why, the proof of this is a little cumbersome, all right? So the cross product is given, okay? Now, one thing I want you to look at is what is included in each of the individual components and what is not included in each of the individual components. So the x component of this product is given by y1 times z2 minus z1 times y2. So this is just the x component of this vector, okay? Next comes the y component of the vector, which is going to be z1 times x2 minus x1 times z2. So this is the y component, and the z component of this vector is going to be x1 times y2 minus y1 minus x2. And this vector here, using the components, so not surprisingly, this is what we're going to call our algebraic definition of the cross product, all right? Because it only works with the components of the individual vectors. It doesn't rely on the angles between them. Gives us a vector which is going to be perpendicular to both u and v. All right, So let's start with the first thing, okay? Is there two subtraction signs in the Z? Oh, no, thank you. Good call there. I don't know why I wrote that there. Okay, thank you. Good catch. That's a multiplication. Okay. So the first thing I want you to notice, okay, is I want you to look at the X component of the cross product. Do you notice anything about the X component of the cross product? There's no X. What about the Y component of the cross product? There's no Y. And what about the Z component of the cross product? There's no Z. Okay. Now, interesting, but one of the reasons why I bring this up is because I would imagine you're looking at this formula and saying that is not the most, obvious or intuitive formula that you've ever seen in mathematics. The formula for the dot product was, I would say fairly intuitive, knowing that it was going to give you a scalar quantity. This does not look particularly intuitive, okay? So what I'm going to do is I'm going to show you one of the many sort of memory aids for remembering the cross product. It's the one I prefer, the one I think is simplest, but find whatever works for you. So the textbook has an alternate trick for remembering the cross product. You can look online. There's a whole bunch of different tricks people use to remember the cross product. So use whichever one works for you. All right. So let me show you my trick. Okay. So my trick is I place the two vectors one on top of the other. So x1, y1, z1. Okay. And then x2, y2, z2. And you'll see in a second why I do this is I take the x components and I rewrite them to the right of the z's. Okay. And now let's see what I do to determine these expressions. So what I'm going to do to find my x component, remember, there's no x component in the cross product's x component. So I cover that up and look what we have. y1 times z2 minus z1 times y2. Exactly the first expression. So this, you subtract them, and this gives you your x component. Then you move and you hide the y components. And look what we have. z1 x2 minus x1 z2. Exactly the y component there. So again, I subtract these, and this gives me the y component. Then I go back around and I hide my z's, and look what I end up with. x1 y2 minus y1 x2. So subtract them. This is my z component. Okay, so hide the x to calculate the x component, hide the y to calculate the y component, and hide the z to calculate the z component. And it's just this crosswise process. You cross towards the right minus the cross towards the left. And that gives you the exact expression there. Okay? So like I said, this is one of many tricks. Unless you have a really, really good memory, you got one of those photographic memories, that's perfectly fine. You can just remember the formula as is, okay? But I would strongly recommend that you, that you use one of these memory tricks, okay? So let's just recall what U cross V gives me. U cross V, okay, is one vector perpendicular to both U and V. Okay? Keep in mind that this is one possible vector. Okay, this is the one that they chose as the representative perpendicular vector, but it is by no means the only vector that's perpendicular to U and V. So in the next example, they're going to ask you to find the cross product, but then use that to find other vectors that are perpendicular. All right, so are there any questions here before we move on to the example?
Yeah, Tony.
Yeah.
So when, say, determining the y product, does it have to be z1 times x2 minus x1 times z2? Or would
Well,
would like Z2 times X1 give you a different result?
so because there's a subtraction, yes, it would. Does it matter if these two things are interchanged? If I wrote Z2Y1, that
No.
wouldn't make a change but if these two are switched around, yes, it will definitely make a difference. And in fact, you might even think about what that tells you about this product, given that if I switch the orders around, this subtraction is going to cause a different result. Okay, we'll actually get to that. It'll be in one of the exercises later on, but you might even think beforehand what that might produce. Okay.
If you swapped around each one,
Yeah.
so like you swap the order of each one, would it also give you like a workable answer?
So let's leave that for now. Okay.
Oh,
I want it to stew in everybody's brain. Okay. So we'll talk about that in a little bit. Okay. Anything else you want to ask about the? So again, here I'm not proving this. Just trust me. It's not a particular fun proof. I like doing fun proofs. The dot product one was nice because it's just a nice application of trigonometry. This one here is just a lot of annoying algebra. Okay. So what we're going to do now is you're going to go to this question here, and I'm going to ask you to apply the cross product to these two vectors, but then I want you to just confirm that it indeed does give you a vector that's perpendicular to both. And real quickly, how are you going to check that it gives you a vector perpendicular to both? What can you do really quickly to check that two vectors are perpendicular? Take the dot product. Okay, so I'll leave this here, and I'll leave the in case you haven't written it down. Again, when we're doing these lessons, it's very good for you. Ideally, you are kind of taking down the solutions to these questions, but work on this here, and then it asks you to determine three other vectors which are perpendicular to both u and v. And notice how I leave you very, very little space. Okay, and that's because you shouldn't be doing a lot of work to determine these other vectors. Okay, so let me give you a couple of minutes to do this here. So start by practicing cross product. Do a quick confirmation that that result is perpendicular to both u and v, and then come up with three other vectors. Okay, I'll be back in maybe 2-3 minutes. Okay, so we're back. So let me go ahead, and you can check that you did this correctly here. So again, you're going to see me always using my little trick here. So I'm going to place my two vectors one on top of the other. So 2, 3, -4, and then here -6, 3, 8. And then I'm going to take this x column and recreate it on that side. Okay, so if I want to find u cross v, this new vector, so I'm going to hide the x. So what do we have? Looks like we've got 24 minus -12. So 24 plus 12, that's 36. Okay, let's hide the y. So here looks like we've got positive 24 minus 16. So that's going to be 8. And then here, let's hide the z. So we've got 6 minus -18. So 6 plus 18 gives me 24. Okay, so you see I did that, and again, you just get really quick. The main thing here is to just not make sign errors. That's what it's all about. If you want to use a calculator to do these calculations, you might as well go ahead and do it. But it's a fairly quick process. I mean, remember what we did back here to find a vector perpendicular to both. So this certainly was a worthwhile invention here. Okay, so now really quickly, let's check that it's indeed perpendicular to both of these vectors. So let's take 36, 8, 24, and let's dot it with 2, 3, -4. Okay, and let's test this out. And in fact, I'm not even going to waste my time trying to do this in my head. Let's try to do it quickly here. So we have 36 times 2, 36 times 2, plus 8 times 3, plus 24 times -4. And there we go. We get 0. So check, it's perpendicular to the first vector. Now let's do 36, 8, 24, and let's dot it with negative 6, 3, 8. And let's see what we get here. Okay, so what do we have? We have 36 times negative 6 plus 8 times 3 plus 24 times 8. And look what we get. We get 0. Okay, so indeed, this vector that we came up with is perpendicular to both of those two vectors. All right, so now in the next part, I ask you to give me 3 other vectors which are perpendicular. And I think we've kind of already made some reference to this here, but what should be special about all these other vectors that are perpendicular to both u and v? So, okay, so what's being suggested here is that any scalar multiple of this vector should be perpendicular to both. So again, if I think of, okay, we'll wait for this to unfreeze. There you go. If these represent my 2 vectors, okay, there's one small vector that's perpendicular to both. But if I just make that longer and longer and longer, it's still perpendicular to both vectors. And even if I take the vector in the other direction, okay, I notice that any multiple is going to be perpendicular to both of those 2 vectors. So essentially what's produced, if I were to think about all these vectors, is what's produced is just all the vectors along that same line. In other words, vectors that are collinear or parallel, those 2 words are interchangeable, are perpendicular to both u and v. Okay, so if I want to come up with other examples, well, I can take negative 36, 8, 24, negative 8, negative 24. Just take the opposite vector. That'll work. You know, I can multiply everything by 2. 72, 16, 48. That would also be perpendicular. Is there one vector that might be nicer than all the others? You know, if I had to pick one vector that was perpendicular to those 2 vectors, that might be, there you go, is make this as simple as possible. Is kind of divide out the lowest common factor. Okay, sorry, the greatest common factor. Okay, which in this case here, well, it looks like it's going to be 4. So here, 9, 2, 3. Sorry, 9, 2, 8. Sorry about that. Not sure what's happening there. Okay, 9, 2, 8 would be, I'd say, the simplest of all possible vectors that's perpendicular to those 2. Yeah.
There's a question. I'm sorry, I'm really confused with 4a. How do you know that? How did you get that those 2 multiplications are equal to 0?
Oh, I applied the dot product. And by the way, thank you, Hisbon and Andrea and Mandiza. I got it wrong twice. I don't know what's happening today. Okay, so what I did here is I just applied the dot product. So what is the dot product? It's the 2 x's multiplied, so 36 times 2. Okay, so that's what I just did in my calculator. Okay, so 36 times 2 plus 8 times 3 plus 24 times negative 4. And when I put this in, I get 0. Okay.
Yeah. And why did you multiply the other 2 vectors by like 2 and negative 6?
Because what I was looking for were vectors that were also perpendicular to u and v. And what I reasoned out is that if I have this vector that's perpendicular to both u and v, then if I double that, it's still going in the same direction. It'll still be perpendicular to both those vectors. Or if I take this vector and then I consider its opposite, it'll also be perpendicular to both u and v. Okay?
Yeah.
So any scalar multiple will also be perpendicular to these 2 vectors. Okay? So if I take the vector that I found, it's perpendicular to both. Let me just take its opposite. It'll still be perpendicular to both. So imagine here.
So you're just doing that to show us.
Yeah. So here, let me just, let's get some scrap paper here. Okay. Say these are my 2 vectors. Again, this would be so much easier to show live, but say these are my two vectors, okay? This vector, stuck again. This vector is perpendicular, right? To both of these two. 90 degrees, 90 degrees. Well, what if I take this vector? Is that also perpendicular to both? There you go.
Yeah.
One is shorter than the other, but they're both in the same direction. So any vector that's parallel to that vector will also be perpendicular. Okay? So that's the idea here, is I can...
So you really don't have to multiply it by 2 or -6 then?
No,
right?
I just, pick these, I just pick these numbers here. Okay? Here I multiplied it by -1. Here I multiplied it by 2. Here I divided it by 4. Now, the reason I'm saying this is the nicest one is because that's as simple as I can get it. I can't get any simpler a scalar multiple. Okay?
Thank you.
Now, that's an interesting question. Somebody's asked, does this work with any two vectors, as it's hard to visualize if they're not on the same plane? Well, I would say you've already answered your own question, because I drew these two vectors. Okay. I drew those vectors. I can draw them. There you go. Here's on the plane. Okay. But let's say I take any two vectors. Can you see that when I have two vectors, they could always be considered to lie on a single plane? If I take those two vectors, they also lie on a single plane. Okay? So in the end, regardless of what my two vectors are, you can think of them as lying on a plane, and then you have a vector that's perpendicular to both. That's perpendicular to that plane. Okay? Unfortunately, that's about as good as I can do as a visualization here. So I'm not sure if that helps. Okay? But again, what I would suggest is take two pens. There's your two, and you should do this at home because it'll be easier to see than on, and then take, a vector that's perpendicular to both of them. And then you realize that a vector that's perpendicular but longer is just going to be a scalar multiple of the first. Okay? So not a bad idea to try to recreate these things. Well, the idea is, remember, you can move vectors anywhere you like, so you might as well put them tail to tail in order to demonstrate this. Okay? All right, so let's let me find my pencil here. All right. So what we have, and we haven't proved it, but we've seen one example where it works perfectly well, that if you use this cross product, you get a vector that's going to be perpendicular to the two given vectors you started with. Okay. Now, not surprisingly, what do we do with this new operation? We start to ask the same questions that we did before. Is it commutative? Is it distributive? What happens when I take the cross product with itself? Okay. So we're not going to go through too many of these. So I'm just going to go through a couple of them here. Okay. And certainly the commutativity one. Now that sort of came up a little while ago, but let's see what happens here. So if I take U cross V, so I'm going to put that first one on top, and then the second one at the bottom. Okay, and I'm not going to find all three, because I think if we find one of them, okay, we're going to see what happens. So let's just find the X component. So there you go. I'm going to use that, and what do we have? We have Y1 Z2 minus Z1 Y2. And similarly for the other ones. Let's see what happens now if I take V cross U. In other words, I put the second one on top, X2, Y2, Z2, and X1, Y1, Z1. Well, if I now apply my rule, what do I end up with here when I do V cross U? I realize that I end up with Y2, Z1 minus Z2, Y1. What's the relationship between that X component and this X component? They're just negatives of each other, okay? Because here, look what happens, is the second term in the above example now becomes the first term in the one below. The second term here is just, oh, sorry, this should have been Z2, Y1. Sorry about that. Sorry, Z2, Y1. Sorry about that. Okay, this term here is the same as that term there. So they're just negatives of each other. They're opposites. Okay, and you can see that the same thing will happen for the Y component and the Z component. So what can we say about U cross V and V cross U? Well, they're not equal to each other, but what relationship do they have if the components are just the negatives of each other? What is the relationship between these two vectors? They're just going to be opposites to each other, okay? Because the X component's going to be the negative, the Y component's going to be the negative, the Z component's going to be negative. They're just opposite to each other, okay? So similar to subtraction, it's what we call anti-commutative, okay? So that kind of brings up that thing that I think Charlie was asking before, is that if I find this vector through the cross product, can I just use the opposite vector as a vector that's perpendicular to both? And the answer is yes, that would also be, okay? But here what we saw in 4b is, in fact, there's many vectors you can use as your vector that's perpendicular to both, okay? So I'll leave these here. I think it won't be too surprising that when you take, U and you cross it with 0, well, what's going to happen with all these multiplications? Well, what's going to happen with all these multiplications? You're just going to get 0 on everything. 0 minus 0, 0 minus 0, 0 minus 0. So that's just going to give you the 0 vector. You're going to see that the same thing is going to happen when you have a vector crossed with itself, okay? That if you put in, if this is also x1, y1, z1, you're just going to end up with, x1, y1 minus y1, x1, which is the same, or y1, z1 minus z1, y1. They're just all going to be equal to 0. But when you think about it, it's not so surprising that if you try to cross a vector from itself, is there only one direction that's going to be perpendicular to both of those vectors? And you realize no, because that's also perpendicular to both vectors, and this is perpendicular to both vectors, and this is perpendicular, and you have lots of directions that are perpendicular to both vectors, okay? So it's not surprising that you would get something that's not particularly useful, all right? Now we'll take a look quickly at the notes later on. We'll see that there's a whole bunch of other nice properties that the cross product has that we're not going to go and prove. Okay, we don't really need to prove them. Okay, I unfortunately, and it was 100% my mistake that I got that late start with all those technical difficulties at the beginning, but I do want to at least do number 6. I won't do number 7. We'll save that for next time, but I do definitely want to do this here. So if you really have to go, you can watch the end of the video, or if you can stick around, that would be great. Okay, so what we have here is we have, again, what we call the algebraic definition for the cross product, okay, because it involves just working with the components of each vector, okay? But just like the dot product has a geometric version. So does the cross product. Okay, so what we're going to look at here, now I will warn you again, this is not something I'm going to prove. I'm going to demonstrate that it works, but I'm not going to prove it. I will warn you though that the proof in the textbook kind of skips some very difficult steps. They just say, oh, from here you can write the next step. It actually takes a lot of work to do that. So the book kind of cheats a little on doing the proof in case you do look at it. Okay, so our geometric definition of the cross product is kind of interesting because the formula is just a formula for the magnitude of that vector. Okay, the way in which you determine the direction of that vector is something we've seen before. Okay, what we've seen is what we called the right-hand rule. So let's say I have my two vectors and I want to find the cross product of this vector using the geometric definition. Okay, well, we're going to see the equation that gives us the magnitude of this vector. Well, the way in which we get the direction is, let's say this is vector u and that's vector v, is we use the right-hand rule. We do put your fingers in the direction of u, curl them in the direction of v, and then the cross product, it goes wherever your thumb is, going upwards. Okay, so direction of u towards direction of v, thumb tells you the direction of the cross product. But wait a minute, if we use that, what happens if we try to do v cross u? Hey, I put my fingers in the direction of v, curl them in the direction of u. Where is my thumb pointing now? Can't sort of see it, but where's my thumb pointing? If I go v u, you see my thumb is going to be pointing in the opposite direction. So this also is a way of, kind of justifying the idea that u cross v and v cross u are opposites of each other. Okay, because we're going to see that the magnitude won't depend on the order, but because you're using the right-hand rule to determine the direction, whether you start with u and go towards v, points up, or if you started with v and went towards u, it would be pointing down. All right, so let's take a look, and I think you'll find this kind of interesting because it will look very familiar. Okay, it's the magnitude of u times the magnitude of v. Is this looking familiar so far? What's this looking like? Well, what's it looking like so far? It's looking a lot like dot product. So it'd be interesting if they were exactly the same magnitude, wouldn't it? Well, it might, but it's not. Okay, it's times the sine of the angle between them. Okay, so theta is angle between u and v. Okay, so we're going to show in a second that this does indeed give you the correct magnitude. Okay, but kind of interesting how you get a very similar equation as you did for the dot product. Okay, but keep in mind, the only thing this gives you is the magnitude of the cross product. So if you forget those magnitude signs and you just write, u cross v is equal to that, that's an incorrect statement. Okay, because this only represents the magnitude. You have to use the right-hand rule in order to determine the direction. Okay, so the last thing we'll do today is we'll quickly show. Didn't we say that the magnitude of cross can be anything? No, but remember, the cross product represents one specific vector, which is perpendicular to both. Okay, oh, I'm glad you brought that up. That's a very distinction. Okay, this vector here is the cross product of u and v, and it is one of the vectors that is perpendicular to both. Okay, you can use that to find other vectors that are perpendicular, but there's one and only one cross product. So remember what I said, if you go through the development of the formula, you see that there's many possible scenarios. There's one particular one that is chosen to represent that thing we call the cross product. Okay, I'm actually glad you brought that up. Okay, there's only one cross product, but then you can use it to come up with other vectors. Yeah, Andrea, don't worry. I want to make sure everybody else gets that, okay? Because that was an excellent, I'm really glad you asked that question, okay? Okay, so let's test it out here. Let's do it algebraically first. So u is 2, 3, -4, okay? And in fact, cross, I'm not even going to write it out because we already did this. It's the same as the one that we had before. And so what was our cross product? It was 36, 8, 24. Okay, 36, 8, 24. And now let's find the magnitude of u cross v. So, yeah, exactly it. Yeah, Jacob, that's why I said looks very familiar, but slightly different. So dot product is cos, cross product is sine. Okay. Okay, so let's look at this magnitude. So square root of 36 squared plus 8 squared plus 24 squared. And we get, look at that, exactly 44. How nice. Okay, so that one was nice and easy. Okay, if I want to calculate using this new geometric definition, okay, so magnitude of u times magnitude of v times sine of theta. Well, magnitude of u is nice and easy. It's just, what do we have? U is 2, 3, 4. So 2 squared is 4, plus 3 squared is 9, plus 16, times magnitude of v. So that's 6 squared is 36, plus 9, plus, what is that? 64. Okay. We need the angle in order to calculate this. How am I going to find the angle between these two vectors? Who's going to remind me how I'm going to find the angle between these two vectors? I'm going to go back and use the dot product. So we'll do that on the side. So u dot v is equal to magnitude of u times magnitude of v times cos theta. Okay. So what's u dot v? Okay, well, u dot v would be -12 plus 3 times 3 is 9, okay, and then minus 32 equals, well, square root of u, we started finding it there. So what do we have? We have 16 plus 9 is 25, plus 4 is 29. And then here, what do we have? We've got 64 and 36. Well, that's 109. Times cos theta. So if we want to calculate theta, let's get our calculator. Okay, so we have cos inverse of, so in the numerator we have -12 plus 9 minus 32. And then in the denominator we have square root of 29 times square root of 109. Okay, and that's 128.5. So now I can finally put this into this equation. Sine of 128.5. And folks, the drum roll, this will say whether what we've done makes any sense. So again, this is square root of 29 times square root of 109 times sine of 128.5, and look at that, 44. Okay, the same answer. Okay, so definitely not a proof. Okay, so the proof is much more involved, and like I said, the textbook kind of skips some very difficult algebraic steps along the way. But this is, we'll take this as a good omen that it worked for this example here. All right. So just to finish off, okay. And again, I do apologize for that delay at the beginning. Okay. So you have this cross product or vector product. which is given by this complicated equation. And what it produces is it produces a vector that's perpendicular to the two original vectors. Okay, this is one trick for remembering the formula. Pick whatever you like. You see that cross product has a lot of the same characteristics as we've seen before. It is distributive under cross product. It's also distributive under, it's associative under scalar multiplication. Doesn't matter where I multiply the k. Okay, it's not quite commutative, but it is anti-commutative. Okay, and this is very important. The cross product is a purely 3D operation. Okay, it's a purely 3D operation. There's no cross product in 2D. All right. And lastly, that if you find the cross product, any scalar multiple of that vector will also be perpendicular to u and v. Obviously not if k is 0. Okay. And then here you've got your geometric definition. Okay. And just in case you're not 100% convinced, here's another example where I show that the geometric and algebraic definitions of the cross product for magnitude are equivalent. Okay, a second example. Okay, anything we want to ask about this here before we go? Yeah, we didn't derive it. So like I said, you can look at the textbook if you want to see the derivation, but the warning I'm giving you is that at one point they say, oh, this step follows from that step. It actually is quite a bit of algebra to get there. So they kind of skip over some tough, but if you want to get a sense of what it is, of what the derivation looks like, you can take a look at the textbook. Okay.